Okay, so test. Hold on. Test. Test. Okay, so another debug stream, or not really debug, but more messing around with it stream. So we'll fire up Doom on my FPGA prototype. This time I am running it at a faster, or at a slightly faster clock speed. Doesn't technically pass timing at these speeds, and it does have some bugs, but it does go a tiny bit faster. As otherwise mostly sitting around trying to see if I can improve the performance situation at all, but yeah, it is possibly a little bit faster than it was before. Uh, um, yeah. This time I also have a small external speaker hooked up to it as well, so there is some audio at least. I wouldn't normally be using speakers, but works well for demonstration. But audio quality isn't really great. Been meaning to debug that still. And the MIDI playback still doesn't work for some reason. I've not gotten around to debugging that. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Yeah, the one mystery I was trying to figure out is why the performance is as lackluster as it is, because well, at least from what I'm seeing of the hardware stats, it should theoretically be a lot faster than the early 90s PCs that these games were meant to run on. But it could be due to it using a C version of the, or a plain C version of the renderer, or compiler optimization issues, or something. But yeah. But in any case, things like the memory bandwidth and similar should, in theory, be a lot faster than what would have been available from things like 30-pin sims, like what most of the original 386s and similar used. But measured performance is, well, is noted not coming out that much higher than a lot of those 386 era PCs, which is mysterious. There is some improvement due to boosting up the clock speed, but not quite as much as would be expected if it were actually CPU bound. So it's likely it is, or likely performance is bound to a large extent by the performance of the memory bus, but again, as noted, it's still a lot faster than what should have been on a 386. Also, since the last time I tested, I had gone and well, fixed the keyboard issue. It turns out the keyboard issue was mostly due to not having a big enough FIFO. So, like originally I had a FIFO length of 8, and it seems that like when with this intensive keyboard action going on, sometimes it was putting out more bytes than the buffer could handle, and it was hitting the length of the buffer. So, but increasing it to 16 has, well, improved the situation. There is a certain probability of, still a certain probability of random crashes, mostly due to zone corruption and Doom and similar, but that also occurs in the emulator, so it's not really the fault of the CPU core in this case, but some other bug I've not, or some other issue I've not fully resolved. Yeah, I was messing around in episode 2 partly because episode 2 seems to have less maps that are prone to cause memory corruption and crashes. The main map I'd encountered which is most prone to causing memory corruption and crashing was E3M3, but as for why, I've not figured that part out yet. Yeah, Doom 2, like, I think Map 02 and Map 04 have also been somewhat prone to causing memory corruption. Presumably for a related reason, but don't know exactly. Or those were, oh yeah, or those not aware, this is, yeah, this is running off an FPGA and, using a custom made, implementation of a custom made instruction set I am calling BJX2, which, as noted, or can be noted, is basically sort of VLIW and sort of RISC. It's sort of like a RISC, except with the ability to explicitly encode instructions that are to be run in parallel with each other. So, and functionally in that sense, it's more like a VLIW architecture, like something like the Titanium or similar. But it is functionally a bit different than an Titanium as well, because the instructions are composed from multiple 16-bit, or actually multiple 32-bit units in that case, as opposed to multiple 32-bit units as opposed to a single large 128-bit unit. And also because the bundles are themselves variable length. And of course there's the 16-bit scalar instructions as well. So it's possible, at least for areas where either there's a lack of all that much parallelism, or where performance doesn't matter, you can use 16-bit instructions and get slightly better code density. It seems to have frozen. The PGA temperature is slightly above ambient, but otherwise not much is notable. Sometimes the monitor is prone to not getting the correct timing there, and sometimes I need to restart the monitor multiple times until it gives me the resolution I want. Basically, I'm outputting 640 by 480, not 720 by 400, and when it's 720 by 4, when the monitor thinks it's 720 by 400, then it's not showing the whole screen. But why it's doing that, don't know. Might be because it's just not quite close enough to what the monitor thinks of as 640 by 480. But whatever the case. So Quake has demonstrated quite a bit more issues at the higher clock speed, but yeah. It also shows a little bit more benefit as well, in the sense of, well, frame rates aren't quite as awful. Assuming it works. And assuming it doesn't do the whole, Nintendo 64 cartridge tilting thing, which is what it was doing last time. I could run at intermediate clock speeds, but technically I'd need to use a PLL or something, and a PLL does go outside of the Verilog subset I'm using, because it would require using geometry starting to twitch out a little bit. If I run it at a lower speed, it's a lot more, all the glitches go away, but it also runs at a lower frame rate, which is, as noted, well, not exactly good. The frame rates are not exactly good. Yeah, that's annoying. Oh yeah, but yeah, from earlier remembering, yeah, I could run it at intermediate clock speeds, but I would, yeah, need to use a POL, and that would make it sort of dependent on the Xilinx tools. So yeah. Yeah, but I sort of am trying to write it in a subset that works in both Vivado and in Verilator, so it does impose some restrictions. And temperature is slightly above ambient, so yeah. Oddly enough, with my own CPU core, it's nowhere near, or getting nowhere near as warm as it does when running the actual default Blinky whatever demo. Is And again, I'm not sure how much actual computing power is fused by whatever they're doing in the little Blinky demo, but I do know the Blinky demo does make the FPGA a fair bit warmer than my stuff. So yeah. Similarly, I've not actually tested to see how Quake performs on Microblaze or similar. Um, but yeah, if Quake performed on Microblaze a lot better than this, well then I guess it would be telling, but I've not tested it. And also presumably Xilinx for their stuff would be using all of their features rather than just writing in a, you know, restricted subset of Verilog. Hmm. Oh, it's being surprisingly well behaved this time. Last time I actually was running Quake with it clocked at 100 megahertz. It was starting to go all about like GoldenEye 64 or something. But and it has crashed. I'm going to rebuild the core back for the usual 50 megahertz. Yeah, this is the simulation. It, well, it can run Quake in simulation as well. It's just quite a bit slower. It'll typically take actually about a good solid day to get Quake loaded up and in a map and similar in the simulation. Because that little sparkly there, that's the raster, or that's the raster refresh. So each time it redraws the screen, well, that's the 60th of a second right there. But yeah. And now it's starting its next 60th of a second time slice. As note can be noted, yeah. So simulation redraws at the rate of raster as raster refresh, and so it can be seen it's not very fast. These little statuses here map to basically roughly the equivalent of the LEDs on the FPGA board, and the relative intensity of the LEDs in this case can show where it's spending most of its activity. So these represent basically pipeline stalls in the main processor, and these ones imply it's from the first of the four lanes it can basically get stalls from. So yeah, this one is mostly for waiting on memory or similar. This one is mostly for other pipeline stalls, like things like interlocking and similar, or interlocking and waiting for instructions to complete and similar. Because the memory related ones tended to dominate, I gave them these four little lights over here. So this one is basically instruction cache, waiting for that, and then data cache, which can be seen as a lot more active. These last two ones relate to basically things being sent to external memory. So this basically is request to external memory, and this one is basically hold status, or waiting for either an L2 miss or DRAM. Actually, yeah, L2 miss and DRAM are basically the same thing, but in any case, that's what can be seen here. So, in general, most of the activity is from the data cache, mostly trying to access L2, with DRAM not quite as significant for most of the time, and instruction cache is also not quite as significant. But in general, memory is the majority of the stalls compared with pretty much anything else that can be causing stalls. So that's where performance tends to lie in this. Well, in terms of the processor core. In terms of the code itself, it's mostly because there's a whole lot of memory loads and stores. Doom and Quake themselves consist, well, primarily of memory loads and stores. So synthesis got done. Close that for now. I have my ever-increasing look cost, which is not quite ideal, but it is what it is, I guess. So 43% of the total look budget is used for this FPGA, and slightly over half of the block RAM. Can that be seen? No, that's can't be seen. How can it be seen? Yes, it can be seen. So 43% of LUTs and 52% of block RAM. With this level of LUT utilization on this FPGA, I could actually stick like a whole nother core or something if I wanted, but yeah. But partly I was intending for this to be usable on an RDS7, and so it means it needs to be able to fit. Of course, it's using too much block RAM for an RDS7, but it's not completely used up the LUT budget. Whether or not it passed timing or anything, that's a bit more of an open question there. But then again, when I first moved over to this FPGA, it's actually harder to get stuff to pass timing on this on this here Ardix than it was on the Spartan, but why, don't know exactly, but you know, they should have theoretically been roughly about the same, but at least in terms of Vivado and similar, it was being slightly harder to get things to pass timing on this, but yeah. As can be noted, yes, the whole synthesis and implementation process is fairly slow. No. I think the power usage is stale. That's more, looks more like, yeah, that's for the 100 megahertz core, 0.7 watts. At 50 megahertz it uses a bit less than that. And of course at 100 megahertz, yeah, kind of failed timing pretty bad, but yeah. However, despite failing timing really bad, it still at least manages to sort of work somehow, so that's something. Oh yeah, total delay 13 nanoseconds. Requirement 10 nanoseconds. Did it pass? Nope. Yeah. FM synthesis module. Something doesn't work in it for some reason. And it doesn't seem to be producing output, but haven't got around to really debugging it yet. This is more a case of module that, well, I haven't really unit tested it, but it's also not really easy to unit test well an FM synthesizer either, but yeah. So yeah, it's more a case of, well, I wrote it freehand and it doesn't work for some reason. But generally the way it's supposed to work at least is, well, it would do or it would basically step at 1 megahertz, alternating between channels and mixing those, and at once every 64 kilohertz it will have updated all the channels. So in this case there's about 16 FM channels which it steps through and mixes essentially, or does the math for essentially one channel at a time. Then once it updates and accumulates all the channels, that's what it sends to the output. As can be noted, well, we can't exactly calculate the sign in real time, or yeah, realistically in real time on this, but we can use a lookup table. This case is an 8-bit lookup table, which thinking about it is, oddly enough, I didn't remember it being 8 bits, but yeah, this says it's clearly 8 bits, so yeah. Alright, 6-bit lookup. Thought I'd remember it being 6-bit result as well, but that's not what I'm seeing. Yeah, in any case, probably don't need super high precision for, well, the sign values in an FM synthesis thing. Yeah. So looking at it, yeah, it's 2's complement. Probably not too surprising there. Other news did recently add an experimental new instruction which, well, more or less is a push, pop, and move instruction, but instead of, well, doing narrower values, it does like 128 bits at a time, mostly by using a pair of registers. So using a pair of registers does at least, well, it saves a few clock cycles, but not really that much of a significant influence in this case because the main bottleneck seems to be memory bandwidth as opposed to actually running instructions on the processor, but yeah. The annoying thing is it's like our memory bandwidth is hard to really fix. Well, apart from somewhat redesigning the whole cache system and other stuff like that, and maybe do a faster DDR interface. And that is real time how long it takes to, well, run synthesis for this thing. Meow. Hey, kitty. So Doom again, this time at 50 megahertz. Or about half the clock speed as before. Yeah. And it has crashed. Which is funny because it should be actually more stable at lower clock speed, but unless I need to do a hard power cycle or something, but which is always possible. So it seems this time around it is, well, not being cooperative. So hard cycle it and see what it does. Mm-hmm. Okay, so seems Doom has decided it doesn't want to cooperate anymore. Which basically means, well, not sure. Might have just been something about this particular, um, or how it's synthesized this time, or some by some off chance, like running cores that are outside of, or that had failed timing had somehow interfered with the FPGA's ability to do its FPGA thing, but not sure why it would. and try something else. Only so much I'm willing to tolerate low single-digit frame rates right now. So, what if I summon up the version of the core that's on the FPGA? And see, will Doom cooperate with this one? It should have theoretically been cooperating before, but it's curious. Because I hadn't actually changed anything in the Verilog code since the last time I ran Doom at 50 megahertz, so and the files on the SD card haven't been changed either, so why it has suddenly stopped working is mysterious. This version of the core that's running right now is one from a few days ago, and it has crashed in the same way, which implies something has changed. Mysterious. Guess it is always possible that something might have corrupted something on the SD card or something. But yeah. You know, at least assuming or excluding the possibility of somehow damaging the FPGA, but Alright. So yeah, this still works. And the FPGA does start getting decidedly warmer when it's running this than it does when running my CPU core, but and it crashed. Current guess is probably somehow something's got messed up on the SD card or something, but hmm. Well, it's annoying, but you know. I think I'll probably end the stream about now. But yeah. Technically, stuff is at least sort of working.